present? Okay. Okay, so we are going to start the class 12 topics. The first topic that we will discuss today is the electrostatics portion. So at the beginning of the electrostatics, you will find that there is something analogous, some similarity with the gravitation. Electrostatics is very similar to gravitation. Both are following actually the inverse square nature. Inverse square law is obeyed in both the cases, and both of these are treated as the central force. Central force means it has a tendency to depend only on the position, function of position. It may, in case of gravitation, it is only attraction, but in case of electrostatics, attraction, repulsion, both may happen. Okay, so with this basic knowledge of gravitation, we are going to study the electrostatics topic. The first thing that we have to discuss, electrostatics means the phenomenon exhibited by static charges. In this case, the charges are not moving, charges are static, and the phenomena represented by them is called the electrostatics and studied under electrostatics. There is another part, that is the current electricity, and when the charges move, we consider that current, and then another field will be developed, that is called the magnetic field. So we will discuss those things later on. Now, the first thing that comes in our mind in electrostatics, that what is charge? Because beginning of the electrostatics or any electrical phenomena starts from the notion of the charge. Then if I ask you what is charge, any one of you, what is charge? The thing is that in electrostatics we will learn so many things like Coulomb's law, like Gauss's law, electric potential, electric field, and all these things. But all those concepts will come after you have the concept of charge. So the most basic question of this branch is, what is charge? It is just a property of the material by virtue of which it will show the electrical phenomena. You cannot say anything more about the charge because it is one of the fundamental quantity, or if you consider this is the most primitive quantity to describe electricity. So there is no more fundamental thing than the concept of charge in any electrical branch. So you cannot define charge in terms of the other things. Okay. So introducing this property of charge, which is responsible for all electrical attributes, now we are going to define different aspects of this branch. There are two types of charge we know. One type of charge is considered as the positive charge, another type of charge is considered as negative charge. Two positive charges or two negative charges will always repel each other. One positive and one negative, that is dissimilar variants, will attract each other. Okay. Now, like different branches, electrostatics also follow some basic rules. One such rule is conservation of electric charge. Means total amount of charge of an isolated system is always conserved. Suppose you rub both of your palm, and in this case consider that before this rubbing both of the palm has no charge, and after rubbing if you find that there are 5 positive charge in the left palm, then there will be 5 negative charges on the right palm, and such that the sum will remain 0. So together these two pump, if constitutes an isolated system, then definitely the total amount of charge will remain conserved. So this property is called the conservation of charge. Conservation of electrical charge. Second property that we will discuss is the quantization of the electrical charge. The second property that we will discuss. Now, what is quantization? Quantization means it is quantized in terms of some basic unit of charge. The basic unit of charge that can exist freely in nature is this one, 1.6 into 10 to the power minus 19 Coulomb. So its positive variant is the charge of the proton and its negative variant is the charge of an electron. So this is the smallest amount of charge that can freely exist in nature. Okay. So any amount of charge that you will get will be a large multiple of this one. Means it should be an integer multiple. You cannot get 3.5 E. 3.5 E means 3 complete electron and 1/2 of an electron. That is not possible. Because the minimum amount of charge is predicted as E by 2 is not possible. So that is called the quantization of the charge, and for this we can write Q equal to NE, where any large amount of charge Q is N times E, where N will be an integer. Now there is another concept that we already discovered, that the concept of quark. Concept of quark is already discovered. Suppose, and those quarks have this property, they have charge E by 3, 2E by 3 like this. Now someone can say, okay fine, we know the quark is present, so how can you talk about this? Okay fine, quark cannot exist freely. The smallest amount of charge that can be freely exist in nature, that is the electronic charge or protonic charge. This can exist freely. So whenever you will say that there are some large amount of charge, it will be either the multiple of electrons charge or integer multiple of protons charge, because quark cannot exist freely. Now let us think of a situation if in future someday it is discovered that quark can exist freely. Even then quantization is not destroyed. Then it is quantized in terms of the quark, because you can consider that initially a packet is there which contains 10 biscuits. Then if it is discovered that quark is present, then it may be a packet of containing 4 biscuits. Still, in terms of the small packet, it is integer multiple. So even if quark exist in nature, can exist in nature freely, if we discover that in later future, still quantization will be there, it will not be destroyed, only the amount of smallest possible charge will be decreased. Clear? Now these two are the basic things of the electrostatics branch, and now we will move on to the force law. In this case the force law is given by Coulomb's law, and it is described for the 2-point charges. See, for point charges we can write this one, Coulomb's law. What this says, suppose there are 2 point charges, this is one, this is another one, say Q1, this one is Q2, and they are separated by a distance R. We consider initially they are separated by a distance R and they are present in vacuum. We consider it is free space or vacuum. Okay. Then these two charges will exert force on each other, and according to Coulomb, this force is directly proportional to the product of the two charges. This is inversely proportional to the square of the distance between the charges. This force is directly proportional to the product of the charges. This force is inversely proportional to the square of the charges, square of the distance between the charges. Then we can write mathematically that F proportional to Q1 Q2 divided by R square, and you can employ a constant and write F equal to K Q1 Q2 divided by R square. Now this structure is very similar to the Newton's law of gravitation. Mass is replaced by charge, and the inverse square law is present in both the cases. In case of gravitation, it is in following this inverse square nature. It is also, Coulomb's law is also obeying this inverse square nature. Now, importance is in the inverse square nature, both obeys inverse square nature. Now, there is also some dissimilarities. Dissimilarity is that gravitational force is only attractive in nature. It cannot repel. Whereas Coulomb force can be attractive, can be repulsive. Another thing is that gravitation force does not depend on the medium in which the masses are present, whereas Coulomb force is mass dependent. Coulomb force is medium dependent. It depends on the medium in which the charges are present. Now, which portion of the force is dependent on the medium? This constant K gives the medium dependence. Medium dependence comes through this constant, because in case of gravitation the constant is capital G, called the universal gravitational constant, because at every point, everywhere in this universe, in any medium, the value of capital G will remain same. But the value of this constant K is medium dependent. If you change the medium from vacuum to underwater or under oil, anywhere, inside glass, anywhere, this value of K will change. And once the value of K is affected, the value of the magnitude of the force is also affected. So gravitational force does not depend on the medium, but Coulomb force depends on the medium. So these are the two differences, that Coulomb force allows repulsive nature between two charges. It is a medium dependent force, where gravitation is only attractive in nature and the gravitational force is medium independent. Clear? Now, we want to write the vector formulation of this force. Then we can show, if I consider both the charges are positive or both the charges are negative, the force is directed along this direction. Both positive and both negative. In that case, forces are directed opposite to each other because they are repelling each other. If one charge is positive, another is negative, then force is directed inward but still in the opposite direction. See, still in the opposite direction. If one is positive, other is negative, but now they are attractive in nature. But whatever be, this force acts along the line joining the two charges. This force acts along the line joining the two charges. It may be repulsive in nature, it may be attractive in nature, but whatever be, their direction should be along the line joining the two charges. Means they are obeying the central, this nature is called the central force nature, and they are also obeying Newton's third law of motion. Okay. Since they are obeying this one, so we can write F21 is the force on charge 2 given by charge 1. Similarly, you can consider this one is F12. So in this case, I consider only the repulsive nature and consider both the charges are positive. See, these forces are oppositely directed, and we can readily write F12 is equal to minus F21. Their directions are opposite from each other and their magnitudes are equal. So they are obeying Newton's third law, like gravitation. Now since they are obeying Newton's third law, we can consider that this force Coulomb is a conservative force like gravitational force. So if any particle is moving under this force, we can consider it will obey the conservation of mechanical energy. Like in case of gravitation, if we consider the motion of a particle under gravity, we consider that total mechanical energy of the particle will remain conserved, where mechanical energy, one part is the kinetic energy, other is the gravitational potential energy. So in this case also total mechanical energy will be conserved. One part is kinetic energy, other part is electrostatic potential energy. Okay, and but for that, remember one thing, we are considering electrostatics and we are talking about the particle is moving. Means the particle must move very slowly. Otherwise you cannot consider electrostatics, because if the particle is moving with a high velocity, then you cannot neglect the magnetic effect. You have to consider the presence of the magnetic field in that case. So you have to move the particle very slowly under electrostatic condition, then we can apply the laws of electrostatics and see that this A1 is a conservative field. Clear? Now, so after all these things of Coulomb's law, we will discuss some problem regarding application of the Coulomb's law, and then we will go to the more subtle concepts. See, so how many students are here for the NEET? 49. 49. One increased. See, so we consider both the charges are positive. This distance is given R1. It's a vector. Now, So this charge Q1 exerts a force on charge capital Q, and what is the direction of that force? Direction of that force is this one. Okay, so this is the direction of that force. We consider both the charges are positive. So we consider the force on capital Q due to Q1. Now we consider that we will remove Q1 from its place, far away, up to infinite distance, such that practically Q1 now have no effect on Q. Q1 now have no effect on capital Q. In this condition, we bring another charge Q, small q2 from infinity, and we put it here at a distance R2. Then what will happen? This is also positive charge, so it will exert its own force on capital Q. This is the force F2. So what we have done, first capital Q is present, then we bring some charge and put it at a distance R1, that is Q1. We calculate the force given by Q1 on capital Q, and that is F1. Now we bring the charge Q1 back to infinity, we put it to infinity, then the capital Q is completely free from the effect of Q1. Now we bring another charge Q2 and put it at a distance R2 from capital Q and measure the force on capital Q given by Q2. This force is coming F2. Now I want to bring the charge Q1 back to its original place. So now I will again bring charge Q1 from infinity and put it here. Then what will be the net force on capital Q? How to calculate the net force on capital Q? Vector sum. It is the vector sum. Now I will ask you one more question. So all of us know that this vector sum will be F. So you can write this F will be equal to F1 plus F2. Now I will ask you one question, that is, what is F1? Force exerted by Q1 on capital Q when Q2 is not present. What is F2? Force exerted by Q2 on capital Q when Q1 is not present. Now, who guarantees that when both the charges are placed at a distance R1 and R2 from capital Q, they will remain apply the same force as applied by them before? That the behavior of the force given by Q1 on capital Q You are claiming that this behavior will not change when it finds Q2 in the vicinity. Because F1 is the force given by Q1 on Q when no other charges are present. But now when Q1 is coming back, you are saying that same force as that of the previous value, it is exerting in the same direction, but now the situation is changed. Q2 is present there. So will the presence of Q2 will not alter the force F1? How can you claim that? So what you are basically claiming? You are claiming that force between two charges is not affected by the presence of a third charge. So for doing this vector sum, you have to guarantee that presence of the two charge, force on the two charge is not changed by the presence of the third charge. This type of condition is not there in parallelogram law for vector addition. So how can you add them vectorially? Because if you are giving two contact forces on a particle, suppose someone pulls the particle with a rope, another man pulls it with another rope. These two forces are not affecting each other, but now the forces are field forces. They are affecting each other, and you apply the same law as that applied by the contact forces. In case of contact forces, I can say that I am applying a force here on a particle. Suppose Rakibul is also applying a force on that particle separately. When both of us are pulling that particle, we can say that we can give the same force according to our ability as before. But now they are not contact forces, they are charged particles. So both have the effect so all will affect one another, and still you are claiming that the Q1 exerts the force previously, F1, now in presence of Q2, it will exert the same force. Actually, it is a very problematic situation, and only in case of electrostatics, there is an experimental verification that force between two charges is unaffected by the presence of a third charge. Till date, there is no concrete mathematical proof of this one. It is only experimentally verified in electrostatic cases, and that's why we are lucky, since it is verified. Otherwise, you cannot do the vector sum in this way. That is called the principle of superposition. Most of the time we think that principle of superposition is just parallelogram law of vector addition. That's not true. Principle of superposition is allowing you to add this forces according to the parallelogram law. The law says that force between two static charges, write down principle of linear superposition. Force between two static charges is unaffected by the presence of a third charge. Is unaffected by the presence of a third charge. So this is the principle of linear superposition. Since this guarantees, that's why you can do this vector sum, and remember it's a linear sum, means F1 these forces to find the resultant. Clear? Now we are going to a problem see. There are 2 point charges. One is capital small q, another is 2 small q, and they are separated by a distance r. Separated by a distance r. Both are positive charges. Then, at which point, write down, at what distance from small q, at what distance from small q we can place a third charge, such that it will not experience any force. So you have to find the distance of the third charge from the charge small q, such that that third charge will not experience any force. And the answer will come in terms of r. First tell me the position where to place the third charge is that on this line or outside this line? On this line. Why? Yes? R by? No. Not R by 3. The first part is correct. It should be within this line or on this line, not outside. Now, why it is not outside? Can there be any situation in which this point of not feeling any force lies outside this line? Of course. If one charge is positive, another is negative, then the third recipient of the third charge should be outside this line, means we not within those two charges, it should be outside on that extended part. The null point will be there where net force on that third charge will be 0. But since both the charges are given same sign, so the neutral point will be within this line. Clear? Now check why. See, if I consider this point, I consider both charges positive. So if you place another positive charge, suppose at this point, say capital Q, both the charges will repel this one. So both forces are along this direction, so they have no chance to cancel each other. So null point cannot be here. Okay? Similarly, instead of placing here, if we place here, both the charges will repel to this side. Then neutral point cannot be there. Now if you consider that this charge is placed somehow at this point, then this charge will repel this one, that charge will also repel this one, and they are oppositely directed. So they have the chance to cancel each other if I can properly adjust the position. Okay. So neutral point for the charge capital Q cannot be outside if both of these two given charges are of same sign. Here I said both the charges are positive. If both the charges are negative, same argument will apply. As long as two charges at the two ends are of equal sign, neutral points will be within that line. And if one charge is positive, other is negative, then only the neutral point lies outside. Okay? So write this one. If both the charges are of equal sign, if both the charges are of equal sign, the neutral point for a third charge, lies within that line. Lies within that line connecting the two charges. Okay, so it should not be outside. Okay. See, now I consider that this Q exerts the repulsive force F1, this 2Q exerts the repulsive force F2, and if the third charge Q should be at rest, then in magnitude F1 should be equal to F2. These two forces magnitude should be same. Then only this will cancel each other and you will find that the capital Q will not feel any force. Clear? Now, so for that I can write force exerted by Q1 small q1 capital Q, that is considered as F1. So it will be K Q1 Q divided by, say this distance is x, so by x square. So that x I have to find out. I consider the distance of the third charge from Q is x. Okay, so this one will be K small q capital Q by x square. Then obviously F2 will be K 2Q into capital Q divided by R minus x whole square. Right? It should be R minus x whole square because this part is considered as x. So remaining part is the distance between 2Q and capital Q. That should be R minus x. Okay. Then K cancels, Q, Q, all this cancels. Now we take the square root. 1 by x equal to root 2 by R minus x. 1 by x equal to root 2 by R minus x. Then from this you can write root 2x equal to R minus x, that is root 2 plus 1 into x equal to R. Root 2 plus 1 into x equal to R. So what we will get? X equal to R by root 2 plus 1. Now you can rationalize this one by multiplying it with root 2 minus 1 by root 2 minus 1, and it will give us root 2 minus 1 into R. That is approximately 0.41 R. Not at the midpoint. Okay. So if both the charges at the two ends are Q, then the neutral point will be at midpoint. That is, x should be 0.5 R, means R by 2. Since I increase this charge, then the neutral point shift towards the left. Neutral point will shift towards the smaller charge. Clear? So it will be now at 0.41 R. If you make it 3Q, it will shift further. 4Q, it will shift further. So as one charge will increase, the neutral point will shift away from that larger charge. In this situation where both the charges are of equal sign. Is it clear to everyone? And remember, here when we are taking the square root, I take only the positive square root, because I have already argued that neutral point lies within that line. So value of x cannot be negative. So if you take plus minus, the minus sign will show you the value outside, which is not a true rational result for this problem. Okay. So this is one type of problem which will come from this, and now we will discuss another problem more conceptual than this one. That is also coming many times in NEET, that type of question. So we will discuss that now. Okay. See. We consider 2 point charges. Small q, both are positive at the two ends. Okay. Both are small q. Now write down the problem. 2 point charges, each of plus small q, each of plus small q is separated by a distance, small r, means this distance is considered as small r. Okay, now find the position, comma, sign and magnitude. Find the position, sign and magnitude of a third charge placed on the line such that all charges in the system are in equilibrium. All charges in the system are in equilibrium. Means equilibrium means net force on any charge is zero, not only the third charge, even the force on first and second charge is also zero. Even the force on first, second and third, all the charges will be zero. Then you have to find the position, magnitude and sign of that third charge. Here it is given that these two charges are positive. Should be negative. Then midpoint, sign, magnitude হবে না, প্রথম দুটো ঠিক আছে। Switch on those lights, that tube and the other two tubes. Switch on those lights, this one and those two. Switch on, and this one. So first check what will be the sign of the charge that has to be placed. What is the sign of that third charge? Will it be positive or it should be negative? It should be negative. Why? Acha, okay, I will argue this portion. Check. First I will consider the third charge. So where should it be placed? Exactly at the midpoint, because two charges at the ends are equal in magnitude and same in direction. So third charge should be placed exactly at the midpoint. That is true. Fine. So put it exactly at the midpoint. So first question already comes. The position of the third charge will be at r by 2. Okay, one part is done. Now come to this charge. We consider this is capital Q. Fine. This is capital Q. Now, if capital Q is positive, then this charge will repel capital Q. This charge will also repel capital Q. So net force on capital Q will be 0. If capital Q is negative, so this charge will attract, this charge will attract, but net force is on capital Q is again 0. So from that you cannot determine which charge has to be, what is the sign of capital Q, because capital Q sign positive or negative, both will ensure that force on capital Q should be 0. Then you have to check whether for a particular sign of capital Q, force on the charge at any corner will be 0 or not. So if I consider capital Q to be positive and check what happens to this one, this capital Q will repel this Q. So force on this Q due to capital Q will be along this. This small q will also repel this one. So force on this one is along this. So can these two forces cancel? Can never cancel, because they are along the same direction. So once you consider this capital Q is positive, the forces on the charges at the corner can never be 0. Okay. So because both of these positive charges will repel this one, as a result you can never cancel this. These forces will never cancel each other. Okay. So only option left is that you have to consider that capital Q should be negative. Check what happens. If this capital Q is negative, then this small plus q will repel this plus q with this force, but this minus capital Q will attract. Then these forces are opposite, then they have a chance to cancel each other. Because for the cancellation, at least the force should be in the opposite direction. Then we adjust the magnitude such that magnitudes are equal. Then proper cancellation will be done. But if the forces are not at all directed oppositely, then how can we proceed? So from that we have to find out the sign of the charge capital Q, that it is negative. Then only the forces on the charges at the corner have a chance to cancel each other. But if it is positive, then both the forces on this charge small q will be directed along the same line, so they can never cancel each other. Clear? Now we have to adjust the forces magnitudes. So let us consider this small q will exert a force F1. This capital Q will exert a force of magnitude F2. Now if F1 and F2 are oppositely directed and they have the equal magnitude, then they will cancel each other. We have already argued that capital Q is negative, so these forces are already opposite. Now we will only equate the magnitude. So I will write that F2 equal to F1 and just put what is F2? F2 is the force between capital Q and this small q. So it will be k capital Q small q by distance is d by 2, sorry, r by 2 square. This one will be F1, that is k q divided by r square. So I will not put the minus sign anymore because we have already argued the minus sign. Then this k q, this capital Q will not cancel. This q will cancel, this one q k will cancel, this q will cancel. So it will become capital Q by r square by 4. So it will become q by r square. Okay. So capital Q will become small q by 4. So this is the magnitude. So magnitude of the charge at the middle should be 1/4 of the charge at the corner. Then net force on each charge will be 0. You can take any of the charge. Charges at the middle, charges at the left corner, charges at the right corner. In all the charges, net force will be 0. Okay. Just check all the steps carefully, and if you have any question you can ask. Okay. Last. You. Is it clear? Done? Okay. Now, we consider now this one is a charge Q and it is present here from the beginning. I consider that this charge capital Q is present here from the beginning. Now we consider that another charge Q is taken from infinity through this path and put it here, that is capital Q. I consider for now that all the charges are positive. It is placed at a distance r. Okay, fine. So this charge which is now placed at this point will experience some force. Then this force is drawn here. F. Now if the charge capital Q is not present at that point or not even present around the charge capital Q, small q is present from there at that point from the beginning of our observation, and suppose capital Q is not at all present in the close proximity of the charge small q. Then can you say that if there is no charge small q at this point, there will be no effect of the charge small q at that point? I have the charge small q at its proper place, but if I remove the charge capital Q from that position and take it to infinity, and after that can I say that even if capital Q is not present at that position is completely unaffected by the presence of the charge small q? Or the position of the space at that point is affected by the presence of the charge small q? The force on, that means the force on the charge capital Q is felt, is that fundamental, or the presence of the charge small q changes the property of the space at that point, that is fundamental? Which one is fundamental? The force feeling by capital Q is fundamental, or the presence of the charge small q close to that point is fundamental? And small q will spread its own effect around it. Is that spreading of the effect fundamental, or the feeling of the force is fundamental? Which one? Which one is fundamental? Force, spreading of the effect, because that is called the electric field. So that is more fundamental. Force is a secondary phenomena. So what will happen, and in this context we will write this charge small q as the source charge, and at this point this is considered as the test charge. So the presence of the source charge is more fundamental, and whenever there is a charge present as a source charge will spread its effect in the region around it. That region where its influence is felt is called the electric field. At any point, the strength of its influence is measured by the physical quantity called electric field intensity. Remember, electric field is not a measurable quantity. Electric field is the influence of the source charge that is spread around the source charge, and up to which distance it should spread, up to infinity. But at any point, what will be the strength of its field? That is measured by a physical quantity called electric field intensity. In the slopey language, when we consider that calculate electric field, we say calculate electric field. Okay, so calculate, not the calculate electric field, it should be calculate electric field intensity at a point. But in the common day language use, we can use that calculate electric field. So electric field intensity is a secondary phenomena. First, electric field present, that's why there is some field intensity, and whenever any test charge enters into that field, this test charge is actually interacting with this field and feels some electrical force. So force comes as a secondary phenomena, field spreading is the primary phenomena. So electric field is more fundamental concept than the electrical force. Clear? Now, even if there is no test charge, there is the presence of the influence of the source charge in the space around the source charge, and that space of influence is called the electric field. At any point, what will be the strength of that influence? That is measured by electric field intensity. and once a test particle enters into that position, it will experience some electrical force. Clear? Now, then we can write simply that electric field by dividing this force by magnitude of the test charge that we have taken. So that is force per unit test charge is the electric field intensity at a point. So dividing by capital Q will give you K small q by R square R cap. So what we are doing? We are writing E equal to F by capital Q. E equal to F by capital Q. That is force per unit test charge. Okay. Force per unit test charge is a measure of electrical field intensity. Hey, what are you eating? Okay. So, next we will discuss one thing, that is these two steps I have written, last two lines, both are representing electric field. Are they representing electric field intensity? Are they representing the same electric field intensity or different thing? Are both the formulas will give you the same result, or both the formulas will give you different result? Or is there any difference between these two formulas of electric field intensity? Both I have written as E. Now you are saying, what kind of problem is this? See, this force divided by capital Q, then F by capital Q is written as E. You have written only a mathematical step, and now you are claiming, saying that is there any difference between these mathematical steps or not? Okay, then I will give you one problem. Write down. Calculate the magnitude of electric field intensity. Calculate the magnitude of electric field intensity from a 1 Coulomb positive charge. 1 Coulomb positive charge at a distance 1 meter, at a distance 1 meter in vacuum. Okay, so what are given? See, I have given that the magnitude of the source charge is 1 Coulomb, distance at which the field should be determined is 1 meter, and for vacuum K is 9 into 10 to the power 9 SI unit. SI unit means Newton meter square per Coulomb square. That is the SI unit of force. So Newton meter square per Coulomb square is the SI unit of, SI unit of K. So if you calculate this one, you will get the electric field in Newton per Coulomb unit. Newton per Coulomb. So just calculate. Which formula you will use? See, all the data are given. So we have to calculate only the magnitude. So E should be equal to KQ by R square. The value of K given, Q given, R given. So what is coming? 9 into 10 to the power 9 Newton per Coulomb. This is the electric field intensity at a distance 1 meter from 1 Coulomb charge, positive charge placed in vacuum. Okay. Is there any problem regarding this question? Okay, now I will give you the second question. Measure the magnitude of electric field intensity. Measure the magnitude of electric field intensity from 1 Coulomb positive charge, from 1 Coulomb positive charge at a distance 1 meter in vacuum. Is there any difference in the two problems? Yes. What is that difference? What is the difference between these two problems? It seems same, but it is not same. You can't find what is the difference? Okay, I will give you one very common example. Who is this program's leader? What is the name of the program leader? Murthy sir. Murthy sir prepare all the routines and all these things for you, and Murthy sir told me that it is the duty of the students not to eat between the classes, not to sleep inside the classes, and this is the rule for the students. Okay? And so I thought that he was perfectly correct, and that is the according to the theory. But in the exact practical, we are getting opposite results. So the same thing for these two problems. First one is calculate. Second one, I use the term measure. Measure means some practical measurement. Practical measurements and theoretical expectations are not always correct, same. Okay. So previously, what first problem, what you have done, you have said that there is 1 coulomb positive charge at a distance 1 meter. You have to find the field intensity in vacuum. You put the result in the formula. You are not examining anything, or you are not experimenting. You are calculating what will be the expected value. But second case, you have to measure. So you have 1 coulomb positive charge. Now you have to bring a test charge and put it at a distance 1 meter. Then you have to measure the force on that test charge, and then divide this force with the magnitudes of the test charge. Remember, force should not be calculated by the Coulomb's law. Force should be measured by some apparatus. So physical apparatus is involved. And are you sure that these two results for the calculation and the experimental measurement will be same 100%? There may be some error in the device. If I consider, okay, fine, I have some device to measure the force which is 100% correct, still it is not possible. Why? Because what you have to measure? The electric field intensity of the first charge, 1 coulomb, and what you bring? Another charge. So that charge has its own effect. So both the charges will affect each other. So as a result, you will now measure the disturbed field of the first charge. Disturbed field. Modi cannot show its full field in West Bengal because Mamata Banerjee's effect is there. So like that. So to measure the field of Modi, you introduce Mamata Banerjee, who has that much, almost very strong field in West Bengal. So that's why you cannot measure the BJP's field in West Bengal. Okay, so that is the situation. So you have to bring something else. Suppose your charge is 1 coulomb and you bring another 1 coulomb charge. So I can say that both will disturb each other by 50%. Both will equally disturb each other. So your measured value will have a 50% error. So will this value, if this experiment is successful, if there is a 50% error in the experiment? No. Okay, fine. You will say that, fine, I will take 100 coulomb charge as a test charge and measure the force. Then I will say that your 100 coulomb charge is so strong that 1 coulomb, so it will almost destroy the field of the 1 coulomb charge and you can never measure. I want the undisturbed field. Now you are saying that, okay, I will not bring any charge to disturb. You cannot measure anything because you know only to measure the force by Coulomb's law, nothing else. And according to Newton, everything should be measured on the basis of force. So if you can't measure force, to measure force you have to bring another charge such that it will exert force on that. So you are saying, okay, fine, I will not bring any charge. So that is not fulfilled. The last option is that, okay, I will bring a charge, but it will be very small so that its disturbance will be minimal. So to measure the magnitude of the field intensity from 1 coulomb charge, you can bring 1 proton. That is a good approximation because 1 proton is carrying a charge of 1.6 into 10 to the power minus 19 coulomb, which is very, very, very small than that of a 1 coulomb charge. So in that case we can say that I will disturb the field by a negligible amount. In that case your experimental result and the theoretical calculation will be almost correct. So this term has to be used. Limit capital Q tends to 0. Otherwise these two formula will not give you the correct result, same result. It is similar to a situation, suppose you are saying that there is a thief and you are saying that okay, go to a vacant house, there are so many ornaments, bring 2 bags of ornaments for me. If you can do this, I will declare that you are very efficient thief. So for this no efficiency is required. Anyone can go to the vacant house, put those things, ornaments in the bag and come back. This is the situation where you consider, okay, I will not disturb you anything and I will measure your field. So that is not possible. Second one, you ask that thief, when the military chief is in his office, you will bring his revolver, steal his revolver from him. It is not possible, because when the military chief is in the headquarters and you are going to steal something from the headquarters, so military chief, and he will not at all go to that room. It is not possible. So like that, you are going to measure the field of 1 Coulomb charge and you are bringing 1000 Coulomb. So it will destroy this one. The next thing is that 1 Coulomb charge, you have sent this thief to a particular place, but it is hard that in that particular place there are many thieves like him. So they will fight between each other and cannot show their effect. Only thing is that this is a thief and you send it to a jewelry shop. Suppose there are only two guards are there and they have some stick but not rifle, and by somehow this thief steals something. Then you can say that okay, fine, you are quite eligible. Okay, so the same thing, you have to bring something, but remember, whenever you bring some test charge for the experiment, it will actually a disturbance to the system which you are going to measure. Then you have to ensure also that disturbance should be as small as possible. Otherwise you cannot measure. But if you say that I will not disturb at all, then also you cannot measure. Okay. Now, so this is the concept of the electric field. Now we will discuss some problems. Both charges are plus q and on the perpendicular bisector at a distance small r, find the electric field intensity. Find the electric field intensity on the perpendicular bisector at a distance small r, where distance between the charge is given small d. Question: find the electric field intensity at a distance small r on the perpendicular bisector. At a distance small r on the perpendicular bisector. No, why not? This is for this charge, this is for this charge, but these are not, these are electric field intensity is a vector, so you have to do the vector sum. You are doing the magnitude, addition of magnitude, that is a scalar sum. So either you have to use the vector or you have to split it into components. একটা টু কোথাও মিসিং হয়েছে, টু মিসিং, হ্যাঁ একটা টু মিসিং আছে, ওটা ডাইপোল, আমি দুটো সেম চার্জ দিয়েছি, একটা প্লাস একটা মাইনাস। How to solve this one? See, first consider the field at this point due to any one of this charge. This one, let this magnitude be E1. Okay, E1. So I can calculate the magnitude E1. What is E1? E1 will be K Q by distance square. Distance means that's hypotenuse. That is R square plus D square by 4. This is the because this part is R, this one will be D by 2, so this hypotenuse will be root over of R square plus D square by 4, and since electric field is inverse square, so I have to square this term of hypotenuse, so it will be R square plus D square by 4 only. So that is E1 for any of the charge. Now there is another charge, so that will also produce the same magnitude, field of same magnitude at this point. This will be directed along this. It will be, suppose it will also have magnitude same value E1. I am not putting the vector sign because direction is different, only the magnitudes are same. Clear? Then I will not use the vector sum to find this angle and all these things, rather I will use the component. See, I will consider here this this angle is considered as theta. So this one will be theta. Accordingly, this is also theta. This one is also theta. Okay, because this is perpendicular bisector, so all angles are same. Now we can consider that this will be E1 sin theta. At this side will be E1 cos theta. It is going 3D. So I will write it better. I will write it here. E1 cos theta. Okay, this part. But similarly, I will split this E1 into two components. So this one will be E1 sin theta, and there will be another E1 cos theta in the same direction, in the upward direction. So this term will become 2E1 cos theta. Now see, E1 sin theta parts will cancel each other because they are equal and opposite. E1 sin theta, E1 sin theta. These two will cancel, but E1 cos theta terms will be in the same direction, so they will not cancel, they will add. So resultant field will be 2E1 cos theta. So I can write resultant field E equal to 2E1 cos theta. Okay. Now put the value of E1. So it will be 2kq by r square plus d square by 4. Now, what is cos theta? See, this one is theta. So this one is also theta. This one will be d by 2. Now check this triangle. This one is base. This one is hypotenuse. So cos theta will be base by hypotenuse. Base is with respect to theta. The adjacent side apart from the hypotenuse is called the base. So since we consider this angle to be theta, so this r is the base and hypotenuse is root over of r square plus d square by 4. So value of cos theta will be r by root over of r square plus d square by 4. So together you can write this one as 2kqr divided by r square plus d square by 4 to the power 3 by 2. This is the answer. And in which direction it is directed? Along the perpendicular bisector upward. So if I consider x and y axis, then it is directed along the positive y axis. Okay. Now, I have one question. After all this calculation, how can you check that your calculation is correct, your answer is correct? Sir, I will check the entire procedure from the beginning once again. Not that. There is a technique which will give you whether result is correct or not. Suppose you are starting from a equation and some mistake is done over there, and the mistake is due to that you don't know the correct formula. Then how to remember? See, In this case, if I consider that this R is very greater than D, R is very greater than D, very large, then we can immediately write D square by R square tends to 0. D square by R square tends to 0. Then in comparison with R square, I can put D square tends to 0. In comparison with R square, I can put D square equal to 0. Now see, in this equation, in which term D square and R square, these terms are in sum such that we can compare in the denominator. So I can put denominator D square equal to 0 and see what comes. It will give us 2kqr divided by R square to the power 3 by 2 R cube, 1 R will be cancelled, R square. Write it as k into 2q by R square. Now, this is a check. Why? Let us consider, suppose you have a point charge of magnitude 2q, one point charge, only one, of magnitude 2q, and put it here at the midpoint, and consider that at a distance r, very long distance, at a distance r, what will be its field? K into 2q by R square. From a single point charge, what is Coulomb's law says? E equal to kq by R square. So if the charge has magnitude 2q, then it will be k into 2q by R square. The same result is coming. Now, what is the check in this problem? See, D is fixed and you are saying R is very larger than D. So what happens to you? Suppose this marker, consider this is one charge, this is another charge. This marker distance is D and it is at a distance from his eye. Now I am taking this marker far away, far more. Then what will happen? What he will say about this pen when it is at a long distance? It is just like a point. So two charges overlapped at this point. So as this R is much longer, the gap between these two charges is immaterial. Then you can say that these two charges are almost like a point charge, and at a long distance I am calculating the field for a point charge, and field for a point charge varies with inverse square of the distance, and that is again verified. See, here is no inverse square law, to the power 3 by 2 is coming. But as you are going to the long distance limit, this calculation will give you the inverse square nature, just like a point charge, where the entire charge of this system is concentrated just like a point charge at this center. So if in the long distance limit this is not reduced to the inverse square nature, immediately check the calculation, your problem, your entire calculation, there is something wrong. And if it reduces to the inverse square law in this long distance limit, you are sure that your calculation is correct. There is no error in the calculation. If it will not reduce, then definitely there is something wrong in the calculation. So this is a good check, but not always applicable. There are certain cases where this technique will fail. Okay, so some break required. Okay, only 5-minute break. 5 times 10 हो जावे. It is like elastic property. Now one charge is plus q, another is minus q. So how to find the field at this point? This one will be a dipole. One charge minus q, another charge plus q. But for the dipole there should be some condition that R is very greater than D. Distance between the two charges should be very small in comparison to that distance R where the field is to be determined. Then it is called a physical dipole. Now let us consider here the force is along this, field is along this direction for this positive charge. For the negative charge, the field is directed along this. This is also of magnitude E1. Okay, so I can split these two fields into two components. Let us consider this angle is theta. So this component is E1, this angle theta, E1 cos theta, and this component is E1 sin theta. Now similarly this E1 can be split into two components. So along this direction the component is E1 cos theta, and along this direction there is another E1 sin theta. So together this will be 2 E1 sin theta. Now check, E1 sin theta components will cancel, E1 cos theta components will cancel each other because they are equal and opposite. So previous problem, when both the charges are positive, then this component survives and this component cancels. Now the different components will survive and the other component will cancel. Okay. Then we can consider that net field magnitude E will be equal to 2 E1 times sin theta. Now this one is d by 2, this part, this one is r, so this hypotenuse will become root over of r square plus d square by 4. So I can calculate this magnitude of E as 2 into E1. What is E1? It is k q by distance square. Distance square means r square plus d square by 4. And as you know, in this case sin theta will be d by 2 divided by hypotenuse. So sin theta means perpendicular by hypotenuse, perpendicular is d by 2, so it will be d by 2 divided by root over of r square plus d square by 4. Okay, right? Now so these two will cancel, so it will be kqd by r square plus d square by 4 to the power 3 by 2. R square plus d square by 4 to the power 3 by 2. Right? Now for this to be a dipole, the condition is R is very greater than D. R is very greater than D. Then this one is converted to a dipole. Then we can put D square equal to 0, not D equal to 0. Remember, then D square tends to 0. Now, then if D square tends to 0, then I can write this expression as E equal to k P by R cube. QD is P, dipole moment. Magnitude of either charge into distance between the charge is called dipole moment. So this dipole moment into R cube. And if you want, you can write this one in vector form. If I consider that upward axis is y axis, this axis is x axis, then I can also write this one in the vector form as E equal to this one with a minus sign. Why minus sign? Because dipole moment is defined as, if there are two charges, minus q plus q, dipole moment is defined like this: P equal to q into d, where d is the distance taken as a vector called the dipole length, and it is directed from negative to positive charge. D is the dipole moment vector directed from negative to positive charge. So that's why I write P vector in front of it a minus sign, because electric field is opposite to dipole moment vector in this perpendicular bisector setup. See, here it is not reduced to 0, not reduced to inverse square law, because previously the sum of the total charge is not 0. Now sum of the total charge 0 means it constitutes a dipole. So whenever for a charge distribution the total sum of the charge is 0, then you cannot reduce it to inverse square law, because that is not a point, it cannot reduce it to a point charge problem, because it's a dipole. For dipole the technique is inverse cube. So don't think that electric field varies only with inverse square. It is varies with 1 by r square or inverse square only for single point charges. Single point charges. For a dipole it varies with 1 by r cube. Another dipole is forming. Repeat. Okay. See, write down. For point charges, field will vary with 1 by r square. For point charges, field will vary with 1 by r square. But for a dipole, field varies with 1 by r cube. Field varies with 1 by r cube. Okay. See, now if the field has to be determined on a point on the axis, not on the perpendicular bisector, then it will be just 2k p by r cube. It is just 2 times. On the bisector it is kp by r cube. On the same axis it will be 2kp by r cube. 2 times. Okay. Now write down one question. from the center of the dipole at a distance x, from the center of the dipole at a distance x, the electric field is E1. Electric field is E1, and for the same dipole on the perpendicular bisector, and for the same dipole on the perpendicular bisector at a distance y, the electric field is E2. Magnitude of the electric field is E2. If E1 and E2 are equal in magnitude, if E1 and E2 are equal in magnitude, then find the ratio x is to y. Find the ratio x is to y. See, on the axis means it will be 2p by r cube. So on the axis the field is E1. So E1 should be equal to 2p by 2kp by r cube. Here r is given x. On the bisector it will be E2, that is kp by y cube. Now it is given that E1 equal to E2. So you can write it as 2kp by x cube equal to kp by y cube. P cancel, p cancel. So it is x cube by y cube, that is equal to 2. So x by y, this one will be 2 to the power 1/3. This is the ratio. Means 2 to the power 1/3 is to 1. 2 to the power 1/3 is to 1. Now these are the parts of the basic calculations of the electric field and all these things. Now we will discuss something about more conceptual part, and then we will go to the continuous charge distribution. First thing is how to represent electric field structure. How to represent electric field structure. Suppose for a point charge, so there is a process as suggested by Faraday. Suppose there is certain point charge, we consider that this point charge is fixed, and we bring another unit positive charge, very small and capable of moving, and we put it at a certain distance from the point charge, very close to it. So this will experience some force, and depending on the sign of this original first charge, that is taken as the source charge, this unit positive charge may feel attractive force, may feel repulsive force. So first we consider that this unit positive charge is feeling repulsive force. So we consider that the source charge is also positive. So I consider a positive charge. So around that I put this charge here, and it will experience some force along this direction. Okay, I will put it here. So it will feel some force along this, it will feel some force along this, it will feel some force along this. Okay, fine. Then similarly I will put it here. So it will feel some force along this. If we place it here, it will feel some force along this, along this, along this. So all these are drawn. Now if I fill all those spaces by this line, it will looks like a circle, but it's actually not a circle, it's a sphere. And this charge plus Q we consider as a black dot is taken as plus Q. This black dot is taken plus Q. And these blue lines are representing the path of movement of the unit positive charge in the field of static charge small q. Okay. Now there are no such line which is filling the space around this charge q. So these are completely imaginary lines. Means if we place some unit positive charge, its path will be like that. So these are imaginary lines. So as predicted by Michael Faraday, these are called the electric field lines. Means the movement of the unit positive charge in the field of unit positive charge which is in the field of positive charge q at rest. So this direction or the path of movement is taken as the electric field lines. Sometimes you may call it electric lines of force, because along this line the force is felt by unit positive charge. But the actual name is electric field lines, not electric lines of forces. If you use the term lines of forces, then in case of electrostatics, electric field lines and electric lines of forces both are same line. That's why there will be no mistake. But if you are going to magnetism and still use the same term magnetic lines of force instead of magnetic field lines, then it is completely wrong. In electrostatics it is true, but in magnetism it is not true. We will discuss that why it is not true. So make it a habit to call these lines not the lines of force, it is the field lines. Now these are imaginary lines. Okay, fine. Now this representation is a pictorial representation of the electric field of the source charge Q, positive charge. Then all the questions about the electric field of the source charge must be included in this representation. So we will check whether all these included in this representation or not. Okay, let us consider this charge is small q. So I draw 8 field lines. If this charge is 2q, how many lines I should draw? 16. Just double, because as the magnitude of the source charge increases, the strength of the field will also increase, and field increases means number of field lines will be more and more. Okay, now, okay, fine, but electric field also has another property, because its formula is kq by r square. So it has another property, that is decreases with distance. Field strength decreases with distance. As distance you are going away from the charge, the field strength will decrease. That is not given in the diagram. The student who represents this diagram, he is not including that in the diagram. So there is another student, he is saying that okay, I can do a better representation like this. This one is my charge, so I consider this one. Okay, fine. He consider also this one. This one. See what this boy is doing. So he is claiming that this is the better representation, because as you are going far away from the charge, the field strength is decreasing. So he is drawing shorter and shorter vectors. Okay. Now whose representation is correct? First one or second one, or more correct? Second one is saying that there is no hint in the first representation that field is decreasing as we are going away from the charge. So that's why he uses this representation. Now whose representation is more correct? First one representation is correct, absolutely. Second one's representation is wrong actually. Why? See, what is the electric field for a point charge? I write the entire form, 1 by 4 pi epsilon naught q by r square. This is considered as k, q by r square, right? Now tell me, where electric field is undefined, where electric field is undefined. If you put r equal to 0, then electric field will be only undefined. Okay? Undefined means you cannot plot that point. See, in this diagram, I draw the lines little bit, keeping little bit gap, because it is undefined at origin on the body of the charge. But see, in this representation, there is many such points where the field is undefined, because he is keeping some gap. So this gap should not be there. Means he is saying that at a distance 1 meter it is undefined, at a distance 1.5 meter it is undefined, at a distance 1.36 meter it is undefined. This is not true, because it is only undefined at 0, but nowhere it is undefined. So in the line, this boy should not put these gaps. So if the boy should not put this gap, then what it becomes? Just the first representation. If he is not allowed to put this gap, then his representation and first representation is not correct, are similar. There is no difference, because if there is a vector and you are putting 3 arrows, or in the vector you are putting 1 arrow, it means the same thing. 3 arrow, putting 3 arrow on the vector will not change anything. You can at your wish put thousands of arrows on a vector, but that will not do anything. Okay. So first representation, second representation are same. Now tell me whether it is included that field is decreased. How field is measured? By measuring force. If the force is stronger, field will be. Just momentarily consider, all these lines are like rigid rods fixed in this setup, and any one of you are said go between these rods, 2 rods, and touch the charge. So first you are going, but as you are going close, the gap between the 2 rods is decreasing, and as a result force on your body will increase. That increases the electric force, and because electric field is increasing as you are going towards the charge. So when the test charge is moving towards the charge, so you can consider that the spacing between the 2 field lines is decreasing. So since the space between 2 field lines decreasing, means field lines are more and more congested, means field is increasing. So in the first representation, field increases with decrease in distance, that is included. There is nothing to worry that in the first representation field is decreasing at a long distance, that is not included. Field is decreasing, that is also away from the charge, field is decreasing, and as you are going close to the charge, field is increasing. That concept is included in the diagram. Clear? Because now if you consider just a sphere and consider another sphere, then on the surface of which sphere the field lines are more congested? Obviously on the surface of the shorter sphere, small sphere, because same lines are coming in this diagram, 8 lines. So through the larger surface area 8 lines are coming, through the smaller surface area same number of lines are coming. So on which surface lines are more congested? On the shorter surface, and shorter surface means small sphere. Small sphere means radius small, so we are close to the charge. So as we are close to the charge, field will increase. As we are going far away, field will decrease. But is that field decreases or increases by following the inverse square law? Is that included in the diagram? The first student's diagram will that include the information not only decrease or increase, it should decrease or increase with inverse square. Some students can say that field is decreasing with 1 by r or 1 by r cube. How do you know that it is decreasing only with 1 by r square? That is another problem. Think about it. It is already included in the first diagram that field is also varying with 1 by r square. That is also included in that simple diagram. How? Okay, see the arguments. Electric field lines E varies with number of electric field intensity E varies with number of field lines, because as the number of field lines increases means the amount of charge will increase. So electric field is directly proportional to the number of field lines. Okay. Now how electric field lines field intensity is defined? It is defined by a quantity number, it is directly proportional to number of field lines per unit area. Just now we have said that on the surface of which sphere the lines are more congested, obviously on the small sphere. So electric field intensity is directly proportional to number of field lines by area. Number of field lines per unit area means if area is small, congestion of the field lines is more, so field intensity will increase. So I can write E proportional to number of field lines per unit area. Then if I write E into area, I have that habit of using marker pen. See, then I can write E into area is directly proportional to number of field lines. So write number of field lines now. Earlier you said with which quantity number of field lines will increase? Amount of charge. Amount of charge. Okay, fine. So E into area directly proportional to amount of charge, this one Q. Amount of charge, this one Q. Now the number of field lines emitted from the charge, does it solely depend on charge or depends on another factor also? Suppose there is 8 lines from Q Coulomb charge, then there are 16 lines you argued from 2 Coulomb charge. There are 24 lines from 3 Coulomb charge. So the number of field lines will depend on the magnitude of charge, or we can say that it is directly proportional, but will the number of field lines solely depend only on the magnitude of charge, or there is another factor on which it also depends? Suppose Q Coulomb charge somewhere produces 8 field lines, somewhere produces 3 field lines. Can it happen? Of course happen. You know that situation. Suppose Q Coulomb charge producing 8 field lines in vacuum. I put entire charge inside water. It's a dielectric. In the dielectric, electric field will decrease. So number of field lines will decrease, because number of field lines representing the electric field strength. So in the dielectric, field lines may be 3. So number of field lines not only depend on a amount of charge, it will also depend on the medium in which the charges are present. So I consider here the vacuum. So I put the proportionality constant as E into area equal to Q by, for vacuum, what is the constant? Permittivity. Now, what we actually get? Gauss's law. I haven't started with that concept of flux or all these things, but E into area is actually the flux. Okay. Now, so this is the charge enclosed by the area. So we can put it Q enclosed in Gauss's law. That's why enclosed is written. Now, with which factor area varies for a sphere? Radius r suppose. Then area should contain, area will be 4 pi r square. See now, E into 4 pi r square equal to Q by epsilon naught. Okay. So if E is not varying with inverse square, then on this side there is a r left. R will not cancel from the left side. Because if inside E there is a term 1 by r square, then that r square and this r square will cancel and produce that charge inside is constant. But suppose you are taking a sphere and inside the sphere you put a charge of 1 Coulomb, and you are saying that if I increase the size of the sphere, the charge inside will change. Is it true? New charge will be produced or charge will be destroyed. So that is violating the first conservation principle, conservation of charge. So charge is constant, it should not vary with the size of the Gaussian surface. Okay. So if E is not varying with 1 by r square, it is varying with suppose 1 by r for a point charge, or with 1 by r cube, still you can say that okay fine, E is varying with 1 by r or E is varying with 1 by r cube. So as we are going far away from the charge, field will decrease. Okay fine, I agree, field will definitely decrease, but that will violate the conservation of charge. Conservation of charge is not maintained in that case. Conservation of charge is only maintained if E for a point charge must vary with 1 by r square only, because if you put here E equal to some constant by r cube, say there is a r left, if you put it is any other power other than 1 by r square, if you put, then there is a r left in the left side of the equation, means This q is a function of r. Q function of r means as you are changing r, you can say new charge will be produced or new charge will be destroyed. Whatever be your movement, you are saying I am going 1 kilometer and new charge will be produced. Can it be true? No. So E should vary with 1 by r square such that the cancellation of r square is possible and q will become constant. Once the q is put inside the surface, you should not say that the charge inside will be produced further or destroyed, because that will violate the conservation of the charge inside an isolated system. Okay. So there is no other scope. So only way then we can write here from here that E equal to Q by 4 pi epsilon naught r square. So from the Gauss's law, Coulomb's law for the field can be derived. Because field is decreasing with distance from the charge, that is not the only condition for the field. You have to remember, this will make this condition that field from the charge will decrease. That must obey the conservation of charge. Conservation of charge is violated and now you are saying that field is decreasing. That will not occur. Okay. So if you put E equal to other than any value, 1 by r, 1 by r cube, 1 by r to the power 4, r square, anything, not 1 by r square, then left side r will not cancel, r will be there. And if r is there, q is a function of r, and I can say that if I change r, new charge will be either created or destroyed. Okay. So this is the most conceptual part of this. Now, the Gauss's law introduced here, I haven't used any integral sign or anything, but it gives us the correct result. Why? I haven't calculated any integral or anything, but still I am able to derive the Coulomb's law for a point charge here. But actually you know that in the Gauss's law there is a closed integral. I haven't done anything, haven't write that closed integral E dot ds anything anywhere. Or I have used it, but you haven't noticed. What is Gauss's law? In the mathematical form, if you write enclosed charge, I am not writing ENC, it is enclosed. Consider enclosed charge is Q. So this one, sometimes some S is written over here to remind that this is a surface integral. Sometimes this S is not given, double integral sign is given, means surface. Okay. Now, for a sphere, let us consider spherical surface. Charge is here. What will be the value of the electric field at this point? Suppose E at a distance r. At this point, what is the value of electric field? Everywhere the value of the electric field on the surface of the sphere is E, if the charge is at the center. So then can I write from this? This is actually closed integral. E dot ds means magnitude of E, magnitude of ds into cos theta. What is the value of theta? Theta is the angle between E vector and elemental area vector. Elemental area. Check. This is elemental area ds. So what will be the direction of field at this point? This one. The elemental area vector has the direction same. Elemental area, how it is defined? Cross product of this area. So direction is along this. So electric field is perpendicular to the area, means angle between electric field vector and area vector is not 90, means it is 0. See, with this surface, if you consider this angle, that is 90 degree, but Gauss law is not talking for this angle. It is talking about the angle between electric field vector and not the magnitude of area. This area vector, this one, and both are directed along the same direction because area is defined by cross product. So both are along the same direction. So angle between them is 0 degree. Q by. So this E is constant at every point. So if anything is constant inside the integration, I can pull it out. Cos 0 will be 1. Then what is the total surface area of the sphere? That closed integral means ds, 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 and you are getting the entire surface area of the sphere. So what is the value? 4 pi. Since E is constant at every point on the surface, if the charge is at the center of the sphere, surface of a sphere, if charge is at the center of the sphere, that's why without doing integral I write E into area. That's why I can write. Okay, I have written that E into area will be equal to Q by epsilon naught directly. Because for other surfaces, if that symmetry is not there, I cannot write. Because Gauss's law, from the Gauss's law, you can find out electric field easily only if the symmetry permits. And here, point charge permits spherical symmetry. So that's why on the surface of sphere at every point, field will be equal if the charge is placed perfectly at the center. If it is off-centered, then you cannot write. Because if it is off-center, see what happens. Suppose the charge is here. Now this point is at shorter distance, this point is at longer distance. Means electric field, if there is E1, there should not be E1, it should be E2. Now you cannot apply for this surface. Still, closed integral E dot ds is 2, equal to Q by epsilon naught, that is true. But you cannot pull E out because at different points on the surface, electric field is not same. Only when at different points it is same, when if it is a point charge, you should place the charge at the center. Then only on the surface of the sphere at every point E will have same magnitude and you can pull magnitude of E out of the integral sign. Otherwise not possible. Since I consider here, that's why I have done it without putting the integration, and it will give us the correct result. Clear? So this pulling out of E is only possible if E is constant over the surface over which we are going to calculate the surface integral. Otherwise it is not possible. So flux calculation Q by epsilon naught will always give you the correct result, whether its symmetry permits or not. But field calculation from the Gauss's law will only help you if there is symmetry. If there is no symmetry in the field calculation, you will not get any help. So write this point. If there is no symmetry on the electric field, if there is no symmetry on the electric field on the boundary of the on the closed surface, still Gauss's law is true. For a charge enclosed in the surface, for a charge enclosed in that surface. Means flux is same Q by epsilon naught. Flux is same Q by epsilon naught. But field calculation is not easy because we cannot pull E. We cannot pull E out of the integral. We cannot pull E out of the integral. Because in this calculation, after pulling E, it is easier because I can write the entire surface area directly without integration from the result of mensuration. That is, surface area of a sphere is 4 pi r square. That is a formula from mensuration. So since I can use that one to bypass the integral, that's why the problem solving is easier. But if that is not permitting, that means E is not constant, then you cannot apply only the area calculation by mensuration, then it is not easier to calculate the field. But flux calculation is always possible. Clear? Now, what do we mean by electric flux? Again?
Electric flux is a number of electric lines across.
Acha, okay, is directly proportional to the number of field lines, not exactly the number of field lines. Because see, from a point charge, how many lines you can draw? From 1 Coulomb charge, how many lines you can draw? Or 1 proton, how many lines? 1. Why? Since it is a point charge, field will be in all direction. Suppose I said that I can draw 8 lines. You can draw 30 lines. Someone is saying I am more energetic, I will draw 1000 lines. Okay, fine. Someone will say 5000 lines. So that's why it is proportional, not equal. Then what flux means normally, apart from the electrostatics? What flux means? Flux is related to something. You have read this one. Torricelli is a flux velocity. Flux means something is flowing. Something is flowing. Whenever we discuss the viscosity, in that case we are considering equation of continuity. and in that case I show you that if there is a small pinhole made at the bottom of a tank, the water is rushing through them with a velocity √2gh, which is called the Torricelli's efflux velocity. So efflux means outflow, so flux means something is flowing. So that's why two types of thing is measured. One is influx, considered as negative, another is outflux, considered as positive. So if you are taking a positive charge, the field lines are going out, that is called the outflux, they can produce the outflux. And if there is a negative charge, field lines are converging to it, means it is can produce influx. Now flux, suppose you are considering a point charge and field lines are coming out, through which area you are measuring? Suppose I calculate it through a small sphere, you can calculate it through a large sphere, but since it is coming from the same amount of charge, we must agree that the rate of outflow should be same for you and me both. I am considering a smaller sphere, you are considering a larger sphere, but the enclosed charge remain same, means the rate of outflow should be same for both of us. So that is not the field, because field for me and you are different, because I am calculating over a small surface, you are calculating over a longer surface, so you are getting less value of the field. So something has to convert your less value to a higher value such that the amount of charge will be same, because you and me both have to agree